Lower panel and rocker panel stone chipping is one of the most aggressive real-world durability challenges for automotive coatings because it combines repeated mechanical impact with continuous environmental exposure. Unlike isolated stone hits on flat panels, rocker panels operate in a high-energy zone where debris, water, sand, salt, and temperature cycles act together throughout the vehicle's life. Rocker panels are positioned directly in the wheel splash zone, where tires accelerate stones and abrasive particles at high velocity. Each impact delivers concentrated kinetic energy into a small surface area. If the coating system cannot absorb or dissipate this energy, localized cracking occurs immediately. Even when damage is not visually apparent, microfractures form within the clear coat and base coat layers, weakening the protective barrier. Film build plays a decisive role in stone chip resistance. OEM specifications deliberately increase total film thickness on rocker panels compared to upper body surfaces. However, achieving uniform thickness is difficult due to geometry, spray angle limitations, and line speed constraints. Thin spots become preferential chip initiation sites. Conversely, excessive build increases internal stress and brittleness, which can worsen chipping severity under repeated impact. Primer design is critical in these zones. Chip-resistant primers often incorporate elastomeric components that improve energy absorption and distribute impact stress across a wider area. These primers act as mechanical shock absorbers beneath the decorative layers. Without sufficient primer flexibility, the clear coat and base coat are forced to absorb impact energy directly, resulting in brittle fracture. Crosslink density must be carefully balanced. Highly crosslink systems offer excellent chemical and mar resistance, but lack elongation, making them vulnerable to impact cracking. Lower crosslink density increases flexibility, but reduces hardness and abrasion resistance. OEM formulations optimize this balance specifically for lower body applications, often differing from upper panel chemistry even within the same vehicle. Environmental exposure dramatically amplifies damage progression. Once a stone chip penetrates the coating stack, bare metal or weakly protected primer is exposed. Water, road salts, and contaminants rapidly infiltrate the damaged area, initiating corrosion beneath the surrounding intact coating. Freeze-thaw cycles expand trap moisture, widening cracks and accelerating delamination. This is why stone chips on rocker panels evolve into corrosion much faster than similar damage on higher panels. Additives contribute to resistance, but have defined limits. Impact modifiers and flexibilizers improve crack resistance by increasing elongation and reducing stress concentration. Flow and leveling agents ensure consistent film distribution, reducing thin spots. Corrosion inhibitors slow post-chip corrosion progression, but cannot prevent ingress once the coating is breached. No additive can fully compensate for inadequate film build or severe mechanical assault. Substrate stiffness influences damage severity. Rocker panels are structural elements and experience chassis flex during driving. Dynamic bending adds tensile stress to the coating at the moment of impact, increasing fracture probability. Weld seams, fold lines, and reinforcement transitions further concentrate stress, explaining why chips cluster along specific zones rather than appearing uniformly. Detection of stone chip vulnerability involves both laboratory and field testing. Gravelometer testing simulates repeated high-velocity impacts, while cyclic corrosion tests evaluate post-chip corrosion resistance. OEM engineers correlate lab results with field data from diverse climates to ensure coatings survive combined mechanical and environmental exposure over the intended service life. From a troubleshooting perspective, addressing rocker panel chipping requires a system-level approach. Engineers evaluate primer flexibility, total film build, curing profiles, spray uniformity, and substrate geometry. Process adjustments may include localized film build increases, modified spray paths, or application of protective coatings or films in high-risk areas. Lower panel and rocker panel chipping is not a single defect, but a failure cascade. Mechanical impact initiates damage, environmental exposure accelerates degradation, and geometry dictates progression paths. Successful OEM solutions acknowledge this synergy and design coatings that absorb energy, resist crack propagation, and delay corrosion even after inevitable mechanical damage occurs. If you've noticed repeated stone chipping, paint loss, or early corrosion on rocker panels or lower doors, leave your questions in the comments. In the next episode, we'll continue with stress and corrosion failures at welded joints and panel connections, building further on this mechanical-environmental interaction.